Hello. So, today we will talk about electric field due to cylindrical symmetric charge distribution. So, last class we talked about spherical symmetric charge distribution. So, just like in spherical symmetric charge distribution, we saw that charge should be distributed over the spherical surface and the charge density should either be function of r or it should be constant. Similarly, in case of cylindrical symmetric charge distribution, the condition to apply Gauss law is that charge should be distributed over the cylinder and rho should either be function of r or it should be constant. So, as we know that in cylindrical symmetry, rho is function of r, phi and z. So here, in order to apply Gauss law, it should either be function of r or it should be constant. So, here you can see in the figure that suppose there is a cylinder and if we place x as 4 observer, then all would observe and calculate the same amount of electric field. So there is a cylindrical symmetry. So we can apply Gauss law here. And what would be mm, the mathematical form of Gauss law? It should be surface integral of E dot ds equal to q enclosed by epsilon naught. Now you should remember that E dot ds, so since all observer will calculate the same amount of electric field, that means electric field will be a kind of constant here and it will come out of integration, and the integral of ds would be 2 pi r l, and here in our case we will take the length of the cylinder to be unity, so L equal to 1. That's why wherever we will be taking E dot ds, so it should come out to be E into 2 pi r into L, and that's L should be equal to 1. So let's see. We'll now use this result to find electric field due to an infinitely long cylinder of radius r having uniform surface charge density rho equal to rho naught r. So first we will calculate the electric field at an inside point, then at outside point. So for calculating the electric field at an inside point, we draw a Gaussian cylinder of radius small r and length L, and applying Gauss law we get double integral of E dot ds equal to q enclosed by epsilon naught, and that should be E into 2 pi r into 1 equal to 1 by epsilon naught integration from 0 to r rho naught r into 2 pi r into 1 dr, and upon solving we get electric field E equal to rho naught by 3 epsilon naught into r square r cap. Similarly, for calculating electric field at an outside point, we draw a Gaussian cylinder of radius r and length unity, and applying Gauss law we get E dot ds equal to q enclosed by epsilon naught. So that comes out to be E into 2 pi r into length of this Gaussian cylinder is 1. So 2 pi r into 1 equal to 1 by epsilon naught. Now integration would be 0 to capital R, because charge is distributed up to the cylinder only, up to the original cylinder of radius capital R. So integration would be up to 0 to R, 0 to capital R, and it should be rho should be replaced with rho naught into R, which we have taken in the question, into volume, that is 2 pi r into 1 into dr. So that comes out to be rho naught by 3 epsilon naught r cube by r into r cap. So you can draw the variation of electric field with r, and we get similar as we got in the case of sphere. Now electric field due to hollow cylinder, but this time its rho should be function of rho naught, that is rho should be a constant here and it should be equal to rho naught. So for calculating electric field at an inside point, try to do it as your homework and let's see that how much you will be getting. Did you get it? What you have to solve? you have to find the electric field as we found here. You have to, in the similar way, you have to calculate electric field due to an infinitely long cylinder, but here we have taken volume charge density rho equal to rho naught into r, but you have to take rho equal to rho naught and then you have to calculate. You would get, for inside point you would be getting E equal to rho naught by 2 epsilon naught r cap, and for outside point you would be getting rho naught by 2 epsilon naught r square by r into r cap. Okay, so for inside point what you would be getting, E equal to rho naught by 2 epsilon naught r into r cap, and for outside point you would be getting rho naught by 2 epsilon naught r square by r into r cap. So you have to do it as your homework. Now let's find electric field due to a hollow cylinder at an inside point and outside point. Like we did, we are going in the same way as we went for sphere. There also we calculated first for sphere and then for the spherical cell. So here we have calculated for sphere and now we are going to calculate for we have calculated for cylinder, solid cylinder, and now we are going to calculate for hollow cylinder. So first we would be calculating at an inside point. So in the similar way, we have to take a Gaussian cylinder of radius small r and length should be equal to 1, and applying Gauss law we get double integral of E dot ds equal to q enclosed by epsilon naught. So E into 2 pi r into 1 equal to 1 by epsilon naught integration from 0 to small r 2 pi r dr. Right, 2 pi r dr, and here charge density should be 0 because since it is a hollow cylinder, so all the charge are on its surface, so no charge is enclosed at an inside point. So we get electric field in total at an inside point to be equal to 0. Right, now for outside point, so we take a point outside. In the same cylinder you have to take a point outside and draw a Gaussian cylinder of radius small r, this time greater than capital R, and lengths of the Gaussian cylinder should be unity, and we applying Gauss law we get E dot ds equal to q enclosed by epsilon naught. So E into 2 pi r into 1 equal to 1 by epsilon naught sigma naught into 2 pi r. Upon calculating we get E equal to q upon 2 pi epsilon naught r capital R by small r into r cap. And you can see the variation of electric field versus r as shown. Here up from r equal to 0 to capital R, that is up to the surface of the cylinder, electric field is 0 since no charge is flowed, and outside the hollow cylinder electric field decreases with r. Now write in comment box how will electric field vary with r in case of hollow sphere outside. We have done it in our last lecture. So now let's calculate electric field due to a thick hollow cylinder. So now we are going to discuss about electric field due to thick hollow cylinder. So here inner radius of the cylinder is A and outer radius is B. So for inside point, once again electric field comes out to be 0. Now for R between A and B, what should be the electric field? Applying Gauss law we get E dot ds equal to q enclosed by epsilon naught. So E into 2 pi r into 1 equal to 1 by epsilon naught sigma naught by r, because we have taken surface charge density sigma equal to sigma naught by r, so we will replace sigma by sigma naught by r into 2 pi r into 1 dr integration from 0 to small r. Upon calculating we get E equal to sigma naught by epsilon naught r into r minus a. For r greater than b, once again applying Gauss law we get E dot ds equal to 1 by epsilon naught q enclosed. So E into 2 pi r into 1 equal to 1 by epsilon naught integration from a to b sigma naught by r into 2 pi r into 1 dr. So we get sigma naught by epsilon naught r into b minus a, and once again we have drawn the variation, that is for r equal to 0 to a, electric field is 0. From r equal to a to b, electric field increases with r and then it decreases with r after b. Now let's find electric field due to hollow coaxial thin long charge carrying cylinder. Inner radius is r1, outer radius is r2, and the charge density on the inner and the outer radius are sigma 1 and sigma 2 respectively. So for r less than r1, applying Gauss law, E dot ds equal to q enclosed by epsilon naught. E into 2 pi r into 1 should be equal to 0 because no charge is included. Hence electric field is 0 inside. Now for r between r1 and r2, E dot ds equal to q enclosed by epsilon naught. So E1 into 2 pi r into 1 should be equal to 1 by epsilon naught sigma 1 into 2 pi r1 into 1. So E1 comes out to be sigma 1 by epsilon naught r capital R1 into r cap. For r greater than r2, once again applying Gauss law, E dot ds equal to q enclosed by epsilon naught. E into 2 pi r into 1 should be equal to 1 by epsilon naught sigma 1 into 2 pi r1 into 1 plus sigma 2 into 2 pi r2 into 2. So we get total electric field equal to 1 by epsilon naught r into sigma 1 r1 plus sigma 2 r2 r cap, and that's the variation of the electric field. It is 0 up to r equal to r1. From r equal to r1 to r2, it decreases with r. Once again from r2 to infinity, it decreases with r. Here there is a very important thing, that if you look from inside the cylinder, then you can see that at r equal to r1, if we look from inside the cylinder, then we get electric field to be 0, and from outside if you look, then there is a electric field. That's why at r equal to r1 and at r equal to capital R2, electric field is discontinuous. So you have to keep this in mind. Okay, thank you.